Welcome to solverfy.
For this problem on the topic of oscillators, we are told that a mass is resting on the end of a horizontal spring when it is struck by a hammer, giving it an initial speed. The mass measures 785 grams. A spring has a spring constant of 184 newtons per meter, and the initial speed at which it moves is 2.26 meters per second. Using this information, we want to first determine the period and frequency of the motion, the amplitude, the maximum acceleration, the position as a function of time, the total energy, and the kinetic energy when x is 0.4 times the amplitude. Now, firstly, to find the period and frequency from the mass and spring constant, we know the period t is 2 pi times the square root of m over k. And this is 2 pi times the square root, the mass of the object that is oscillating is 785 grams or 0.785 kg divided by the spring constant of the spring, 184 newtons per meter. So hence we get the period to be 0.4104, or keeping our significant figures, 0.410 seconds. So with the period, it's quite straightforward to find the frequency. The frequency we know is 1 over the period, which is 1 over 0.4104. So the frequency of oscillations is 2.44 hertz. So now we have the period and frequency, and we want to find the amplitude. Now the initial speed is the maximum. The initial speed is the maximum speed, and that can be used to find the amplitude. So this maximum speed Vmax is equal to the amplitude A times the square root of k over m. And so if we rearrange, we get the amplitude A is equal to Vmax times the square root of m over k. And if we substitute our values in, this is 2.26 meters per second times the square root of 0.785 kg over the spring constant, 184 newtons per meter. And so calculating, we get the amplitude to be 0.1476 or 0.148 meters. So that's the answer for part B. For part C, we want to find the maximum acceleration. Now, the maximum acceleration can be found from the mass, spring constant, and amplitude. And this maximum acceleration is the amplitude A times the spring constant k divided by the mass m. And so this is 0.1476 meters, the amplitude, times the spring constant, 184 newtons per meter, divided by the mass, 0.785 kg. So calculating, we get the maximum acceleration of the mass to be 34.6 meters per square second. Next, we want to find the position as a function of time. Now, because the mass started at the equilibrium position at x is equal to 0, the position function will be proportional to the sine function. So x is equal to the amplitude 0.148 meters times the sine of 2 pi times the frequency f, which is 2.437 hertz times t. And so this becomes 0.148 meters times the sine. If we multiply out through the bracket, it's the sine of 4.87 times pi times t. So that's the position as a function of time. Now we want to find, in part E, the total energy. Now the maximum energy is the kinetic energy the object has when it passes through the equilibrium position. So this energy is a half m v max squared. And since we have the mass and the velocity, we can calculate this energy. That's a half times the mass, 0.785 kg, times the maximum speed, 2.26 meters per second, and that's squared. This gives us the maximum energy of the mass to be 2 joules. Lastly, in part F of the problem, we want to find the kinetic energy when x is equal to 0.4a, where a is the amplitude. So we'll use the conservation of mechanical energy for the oscillator. We know E is equal to the elastic potential energy, half kx squared, plus the kinetic energy, a half mv squared, and this must equal the maximum elastic potential energy, a half k a squared. So this implies that a half k times x, which is 0.4 of the amplitude all squared, plus k, the kinetic energy, which we wish to solve for, is equal to a half k a squared. So therefore, the kinetic energy, capital K, is equal to a half k a squared into 1 minus 0.4 squared and this is equal to 2 joules times 0.84, which tells us that the kinetic energy at the point where x is equal to 0.4a is 1.68 joules.